Hello friends, welcome to the video lecture series on digital image processing. I am Dr. Dafda, and in this 7th video class of DIP, we will understand what is spatial and intensity resolution and also its implementation in MATLAB. So what is the meaning of spatial? Spatial means one that is related to plane, image plane itself or image coordinates itself, right? That is X and Y coordinates. So more the coordinates or more the number of pixels or more the number of sampling and divisions, the better will be the spatial resolution and the finer will be the picture. Okay. What is intensity? Intensity means different levels of gray or different shades of gray. So intensity resolution means the resolution which is related with different shades of gray, and it is quite obvious that when the number of shades of gray will increase, again the quality of image will increase. So spatial resolution is the resolution that is related to number of samples or sampling resolution, you can say, and intensity resolution is the resolution that is related to quantization, okay, or the number of gray levels that we are using, and this we have already understood in the previous video class of DIP, that is sampling and quantization. What is MATLAB? MATLAB is a matrix laboratory. So as the name suggests, it is a software that is working on matrices, and you know that our digital image is also a matrix. So MATLAB is most suited for digital image processing. MATLAB is a very high performance language for technical computing. It integrates computation, visualization and programming in an easy to use environment where problems and solutions are expressed in familiar mathematical notation. Okay, so let us go ahead. As we have already understood in the previous class, spatial resolution is related to sampling intervals and sampling, and gray level resolution is related to quantization resolution, right? So inherently, spatial resolution is a measure of the smallest discriminable detail in an image. But mathematically, you can say that spatial resolution can be stated in a number of ways, with line pairs per unit distance and dots or pixels per unit distance being among the most common measures. But to be meaningful, measure of spatial resolution must be stated with respect to spatial units or the image plane units, right? The image size by itself does not tell the complete story, right? To say that an image has a resolution of 512 cross 512 pixels is not a meaningful statement without stating the spatial dimensions encompassed by the image, right? See, it may happen that the image may be of very good pixels, say 1024 cross 1024 pixels, but the image is very big, okay, in size. So at that time 1024 pixels cross 1024 pixel is not enough. At that time you have to further increase the number of pixels for increasing the resolution of the image. And intensity resolution similarly refers to the smallest discriminable change in the intensity level. Based on hardware requirements and considerations, the number of intensity levels usually is an integer power of 2. The most common number is 8-bit image, with 16 bits being used in some applications in which enhancement of specific intensity ranges is necessary, and intensity quantization using 32 bits is very rare. So we will see as we go ahead in this lecture that normally we are using 8-bit images, okay. Even if you go from 8-bit to 16-bit, there is no visual changes in the image due to the resolving capability of our eye. And we have already studied that if you go on increasing the number of intensity levels, the image size will also increase, right? So 8-bit image is a very good image, but what are the number of samples that we are choosing for a particular image depends on the type of image and also the size of the image. So you can see over here, as you go on decreasing the spatial resolution for a particular image, which is say 512 cross 512, when you go down to 256 cross 256, you will not observe any change in the picture because the size of the picture is very small, right? But as you go further down of half of 256, that is 128 cross 128 pixels, you will observe that the checkerboard pattern distortion starts coming in the picture. As you further go down, you will see that the picture starts pixelating, right? So here we have downsampled the image from 512 pixels up to 16 pixels, but of course we have kept the intensity levels at 256. So let us implement this in MATLAB. So this is our MATLAB program for spatial resolution or sampling levels. I here assume that you all have a basic knowledge of MATLAB. So you all know these commands: close all, clear all, CLC. I am reading an image and I am converting the image from color to grayscale image using RGB to gray command, and I will be showing this image in subplot matrix of 2 cross 3, that is out of 6 total I will be showing in the very first portion, and this will be my original image in black and white. Of course the number of pixels will be same. So now what I will be doing, I will be just skipping the alternate rows and columns, alternate rows and column pixels, right, and I will be forming a new matrix I2 and I will be showing the image. So now half of the pixels are removed, so it will become 256 cross 256 pixels image. Similarly, for the third image, I will be choosing every fourth alternate rows and columns and displaying the new image. I can also use the same 1:2:2 and over here, but at that time I have to choose I2 over here in place of I1, but I am choosing my original image, original grayscale image for down conversion, and I will be showing this image which will be of 128 cross 128. And next I will further go down to 128 and then further go down to 1:16 and 1:32. So this I am removing alternate rows and columns. Rather than this, I can also use image resize function, that is the inbuilt function of MATLAB, in which I'll be taking the image and giving the scale of half, 0.5, that is half. That means image will become half the pixels. And similarly, every time I can use image resize function for downsampling the image. So initially I have disabled this statement and we will perform using this mathematical operation. So let us run this program. So this is our output. As you can see here, this is our 512 cross 512 pixels image. Next is 256 cross 256 pixels image. As the image size is small, there is no much change in the details, as you can see. But as you go down, you can observe here that the checkerboard pattern distortion has started coming, and as you go further down, the image starts pixelating, right? So the final image over here is 16 cross 16 pixels. You can even count the number of pixels from here. You can see here these are 16 as well as these also are 16. So this means that as we downsample the image, the resolution becomes worse. Now let us run the same program using IM resize function. Okay, so here I will enable this line and I will disable this line, and let us again run this program. I will get the same output. So you can see here again we can even use image resize function, that is inbuilt function of the MATLAB. Now you can see here in the workspace the size of the images, right? The size of our image I6 is 16 cross 16. So here it is showing 16 cross 16 pixels. You can even see the values of these 16 different pixels, the gray level values of these 16 pixels. So these are the gray level values of the 16 pixels which you can observe in the workspace. So these are 16 pixels over here, as well as these are 16 pixels over here. Similarly, you can see for other images also. For I4 it is 64 pixels by 64 pixels. And you can see the gray level or intensity values. We have kept the gray level or intensity values to 256 constant. That means all the values will be in between 0 to 255. So that is how we do downsampling of an image. Now, what are the effects of this downsampling? Now see, we saw the downsampling of the image in MATLAB. Now what is the effect of this downsampling? Due to downsampling, there may be errors or distortions such as aliasing or checkerboard distortion, which we just saw, right? So Shannon sampling theorem tells us that if the function is sampled at a rate equal to or greater than twice the highest frequency, that means sampling frequency is greater than or equal to twice the modulating frequency, it is possible to recover completely the original function from the samples. But if the function is downsampled, then a phenomena called aliasing, that is distortion, if two patterns or spectrum overlap, the overlap portion is called the aliased portion, corrupts the sampled image. So the corruption is in the form of additional frequency components being introduced in the sampled image, and these are called aliased frequencies, and downsampling results also in a checkerboard pattern due to reduction of samples, right? So that is the effect that is observed when we are doing downsampling. For example, say a car is moving. when you are seeing a moving car in a movie, at that time initially when the speed of the car is low, you will feel that the wheels are moving in clockwise direction. But as the speed of car increases, you will feel that the wheels of the car are moving in the anti-clockwise direction. So why that happens? That happens because the camera that is capturing the image of that car cannot cope up the highest frequency of motion of that wheel. Hence it does the downsampling, and due to this downsampling, the high frequencies start looking like low frequency, and that is the reason why if the wheels are moving in the clockwise direction, we see that the wheels are moving in the anti-clockwise direction, right? So that is regarding the downsampling. But what happens when we want to zoom the image or we want to do upsampling? So for upsampling, we are going to increase the number of pixels. So for zooming an image, we need to do interpolation. Why? Because we need to interpolate the mid values. See, there will be values for the first row and there will be values for the third row. You do not know the values for the second row. So you have to find the values of pixels of the second row, right? So here you need to do interpolation, and interpolation is the process of using the known data to estimate values of unknown location. So this interpolation can be of three types. That is nearest neighbor interpolation, that assigns the value of closest pixel to the new pixel. Of course, it will not be giving very high results. The next one is bilinear interpolation. So this bilinear interpolation considers the closest 2 cross 2 neighborhood of known pixel values surrounding the unknown pixel, and it then takes the weighted average of these 4 pixels to arrive at its final interpolated value, right? So that means it considers 4 nearby pixels. And for bicubic interpolation, it further goes ahead and it considers 16 nearby pixels, right? And then gives the value. So obviously bicubic interpolation will be giving better results in zooming or interpolation as compared to bilinear and nearest neighbor interpolation. But of course, the processing requirements will increase for bicubic interpolation. Okay, so this is how you will find the images using different interpolations. So this is the original image that you will be applying for interpolation. Let us say it is 64 cross 64 pixels image. We have zoomed this image to 512 cross 512 using nearest neighbor interpolation, and you can see here that the pixels are still clearly visible, okay, because we are only considering the nearby values, okay. Whereas if you apply bilinear interpolation, you can see the image is quite good as compared to the nearest neighbor interpolation. And further, if you go ahead to bicubic interpolation, okay, so you can see here that the result is still better as compared to the bilinear interpolation, right? So let us implement this also in MATLAB. Initially, we are reading an image, we are converting that image to single plane image by using IM2 gray. Next, we are resizing this image to 0.25% of its original size, right? So the original image is a 256 cross 256 image, and we are converting it to 1/4 of its portion by using image resize, and we are giving the sample, or we are using the sample of 0.25. That means the 256 cross 256 pixel image will become 64 cross 64 pixel image, and we are showing the original image over here, 64 cross 64 image, right? Next, we are again using the image resize function, and we are resizing this Z2, that is 64 cross 64 pixel, to 512 cross 512 pixel. We are zooming the image, and what we are using here is the nearest neighbor interpolation, and we are showing this particular image. Then again we are zooming the image and using bilinear interpolation and showing that particular image, and finally we are using bicubic interpolation using IM resize. Z2 512 comma 512 will be converting the 64 cross 64 into 512 cross 512, and will be applying bicubic interpolation and will display the image. Let us run this program and see the output. So you can see here, this is our original image. This is the zoomed image to 512 cross 512. This is 64 cross 64. This is zoomed image using nearest neighbor interpolation, and you can clearly see the distortion due to insufficient number of pixels over here. For figure 3, we are using bilinear interpolation. So you can see the quality of this image has increased to a very large level as compared to the nearest neighbor interpolation. And if you further go ahead to bicubic interpolation, you can see the image quality has still improved as compared to both nearest neighbor as well as bilinear interpolation. So that is how we perform the upsampling of the image or zooming of the image. Let us go ahead and understand intensity resolution or gray level resolution. So normally we are using 8-bit resolution, and 8-bit resolution is enough for perceiving capability of human eye. Instead of using 8 bits, if you are using 7 bits for different intensity levels, you can see how the image you will be obtaining. If you further go down to 6 bits, 5 bits, 4 bit, 3 bit, 2 bit and 1 bit, you can see that the image quality goes on decreasing due to decrease in the intensity levels. This is a 512 cross 512 image, which is 8-bit image. Further it is displayed in 7 bit, 6 bit, 5 bit and so on up to 1 bit. So you can see there is not much difference between the 8-bit and the 7-bit, but there is a large difference in between the 8-bit and the 4-bit. After 5-bit, you can see that the artifact starts coming in the image. You can see here that this image has got an imperceptible set of very fine ridge-like structures in the area of constant or nearly constant intensity. And this effect that is caused by the use of insufficient number of intensity levels in smooth areas of a digital image is known as false contouring. Why it is called false contouring? Because the ridges which you can find over here, right? You can see the ridges over here. These ridges resemble to topographic contours of a map. So there are contours in the map, and here there are false contours which you are obtaining in the image. The contours which should not be present and still are present, and therefore this effect is called false contouring effect. Let us implement this in MATLAB. So this program shows the intensity resolution for images or quantization levels for images. We are reading an image. We are converting the color image into grayscale image by using RGB to gray command. Using montage command, we are displaying side by side the color image and the grayscale image. Next, we are getting the number of rows, columns and planes for this grayscale image, right? So number of rows and number of columns, and S will be the number of planes, and the plane number will be only 1 because it is a grayscale image. Next, we are finding out the maximum value of this eye gray image or the grayscale image. So that maximum value will be obviously 255. Why? Because it is 8-bit image which is having values from 0 to 255. Next, we are using a variable b which is ranging from 1 to 8. Why we are using this? Because we want to divide the 8-bit image by different levels as we go ahead. For example, for a 8-bit image, it is 2 raised to 8, that is 256, right? And hence, when you divide by 256, it will give 1-bit image. We are using a for loop in which I am choosing a variable dd which is equal to 1 to length of b, right? So the lengths of b are taken from here. Here I am taking a second variable which is equal to 2 raised to dd. Why I am using this? Because the total number of bits is equal to 2 raised to dd, right? So for a 8-bit image, it will be 2 raised to 8, that is 256, right? Next, what I am doing, I am using a variable z and I am getting the value, or I am dividing each pixel by 2 raised to dd, right? If it is 8, that is 2 raised to 8 which is equal to 256. So I will be dividing each and every pixel by 256 and rounding off the values. So what I have done, I have converted 8-bit intensity levels into 8-bit intensity level divided by again 8-bit intensity level. That means I will get 1-bit image or 1-bit intensity level, and I will be subplotting it using the subplot command, right? And of course I will be giving the title for displaying the number of bits of an image, right? And showing the image. Let us run this program and see what happens. So figure 1 shows the original image and grayscale image in montage, that is side by side. Next, we are displaying the image using 8-bit, then again using the 7-bit, 6-bit, 5-bit, 4-bit, and you can see as we go ahead. See, remember here we are keeping the number of pixels same, right? We are only changing the intensity values. So as we go ahead, you can see the false contouring that starts appearing, or the artifact that starts coming in the picture. So as you go to lowest, okay, the image using 1-bit, that is k is equal to 1. So 2 raised to k is equal to 2 raised to 1, that is equal to 2. That means it will be having only 2 values, that is black and white. So you can see here there are only 2 values, the black value and the white value. For here it is k raised to 2. It is a 2-bit image, that means k raised to 2. So 2 raised to 2, that means it will be having 4 different values. So you can see for this particular image, it is having 4 different values: a black, a white, a dark gray and a little light gray. So in this way, you can change the quantization levels of the image. So as we have learned in the previous video class, if the number of bits of image are less memory will be required to store the image, but you can see the quality of the image will be very bad. You can even see the values, right? So here rows and columns and S, that is plain, right? So what is R? R is 5 and 2, rows are 5 and 2. What is C? Column is also 5 and 2, right? What are the number of planes? S is equal to 1. What is the maximum intensity level in this image, which is equal to M? M is equal to 255, right? And see, the images which we are forming are all of the same size, right? That is 5 and 2 cross 5 and 2, right? Just we are changing the gray level or the intensity levels. So here we have seen the decrease in the intensity level, right? Now you may have question in your mind that what happens if you increase the number of bits from 8 bits to 16 bit to 32 bit and so on. Okay, so let us see the effect for this particular increase in quantization level. So this program shows increasing quantization level, that is making 8-bit image to 16-bit image, increasing the quantization levels from 255, you can say, to 65535, means 0 to 255, and 65535 is 0 to 65535, that is 2 raised to 16, right? So I am again reading an image and converting that image into grayscale image, and then using the inbuilt MATLAB function of image to uint16, I'll be converting my 8-bit image into 16-bit image, and then I'll be showing original image, grayscale image, that is 8-bit image, and my 16-bit image side by side, and we'll be seeing what are the effects. So let us run this program and see. So you can see here, this is our original image, that is color image, grayscale image, that is a single plane 8-bit image, and you can see the grayscale image using 16 bits. Okay, so visually you can see that there is no difference in between the 8-bit image and 16-bit image. That means 8 bits are enough for resolving capability of human eye, and we should not unnecessarily use 16-bit images. Why? It will only result in increase of storage space that is required for storing the image, increase in bandwidth that is required for transmitting the image, as well as increasing processing power for processing the image, right? So you can see that IM is our original image, which is 512 cross 512 image into 3, that is RGNB, because it is a color image, right? Then I gray image is our 512 cross 512 grayscale image, right, which is converted to grayscale, and it is 8-bit image. You can see here uint8, right? And I16 is the image that we have converted to 16 bits, right? So it is 512 cross 512 uint16, that is 16-bit image. Let us see the grayscale values of both the images, that is I gray and I16. So both the images are 512 cross 512 pixels. Let us see the grayscale values of I gray image. So you can see that the grayscale values are varying from 0 to 255. Maximum value will be 255 and minimum value will be 0. So you can see the minimum value over here, that will be complete dark. And even 255, that is complete white, is also present in the image. But all the values are ranging between 0 to 255, as it is a 8-bit image. Now let us see the grayscale values for the 16-bit image that we have converted, I16, right? So you can see that the grayscale values for this I16 image is varying from 0 to 65535. Here many values are larger than 255, and hence it is a 16-bit image. Of course, 0 value is also present, larger than 255 values are also present, and 65535 value is also present in the image, as you can see here. This is 65535. Okay. So using different intensity resolutions, we can use less or more number of grayscales for displaying an image. So that is all for this video lecture. I hope you have gained a good knowledge from this video lecture. Thank you very much.